Let's talk about the Fundamental Theorem of Calculus Part 2 now. This part of the theorem is sometimes also called the evaluation theorem, and we'll see why it's called that pretty quickly here. This one, there's not as much to say about this one as there was about the Fundamental Theorem Part 1. It's pretty straightforward. The first thing let's remember is on the left-hand side of this equation in the Fundamental Theorem is a definite integral. And a definite integral, by definition, must be defined, or is defined, by a Riemann sum. So remember, to compute a definite integral, you have to take the limit as n approaches infinity of the summation, I goes from 1 to capital N, of the function applied at certain test points, f of x I star, and then multiplied by the little, the lengths of the small intervals of your partition that you've taken. So we won't go back into what a Riemann sum is, but the Riemann sum, it's important to remember, is the definition of the definite integral. And definition, there can only be one definition, so it's the definition. And so until we have this theorem, this is the only way we know how to compute a definite integral. So let's look at what the theorem says now. First of all, our first assumption is the same as it was before, which is the function f should be continuous on the interval from a to b. And then the second assumption here for this part of the theorem is that capital F is a known antiderivative of little f on the interval from a to b. Remember, the FTC part 1, the Fundamental Theorem part 1, told us that given the first assumption that f is continuous, we know that little f has an antiderivative big F. It must have one. Okay? Now, if we know how to write down a formula for that, then we're in luck. And hopefully we can use it. Okay, now what does the theorem tell us? Well, these are our two assumptions, right? The theorem then says that the definite integral of little f on that interval where it's defined, which is, remember, the area under the curve of f between the curve and the x-axis, is also computed by or evaluated as the difference between the values of capital F of b and capital F of a. So it's capital F of the upper limit minus capital F of the lower limit. Okay? And so this tells us, if we just sketch a little picture here, here's our x, y axes. Maybe here's A, here's B. Maybe we have some kind of constant, slowly growing curve here. This is our y equals f of x. And we want to compute the area underneath this curve. So the definite integral of this function is the area underneath the curve. And what this theorem tells us is that we can, instead of computing this, maybe our antiderivative starts up here and then does something like this. And what we can actually do then is just evaluate. So if this is our big F of x, antiderivative, we can just evaluate the boundary points of big F. Just find the heights of these two lines and then subtract those two lines, those two heights. Okay? And so this is going to be capital F of B minus capital F of A. And of course, this requires that we know how to write down a formula for capital F, but if we do, it will save us a lot of work. So let's look at a simple example here. Here's y equals x squared on the interval from 0 to 3. Let's start on this one by writing down a formula for the Riemann sum definition of this. Okay, and you might remember that when you write down a Riemann sum definition, you have to chop up your interval into equal pieces. This doesn't look too equal the way I've done it, but let's assume that it is. And so if you chop up your interval into capital N subintervals, then your delta xi is just going to be equal to your difference of your endpoints divided by the number of boxes, capital N. So our delta x, or delta xi, in this case is going to be 3 minus 0 over n, or just 3 over n. Okay, and then I'm sure you remember that as you move from x1 to x2 to x3, we're going to take this equal size step now. And so our xi with a star is going to be equal to a, the starting point, plus delta x times a step, I. Okay, which for this one, the a, the first endpoint, is just 0, and the step size is 3 over n. So our xi with a star is going to be equal to 3I over capital N. And then in our integral, we have, of course, our Riemann sum, we have this term, but we need to plug this term into f. This has to go into the function. Okay, and so f of xi star is going to equal xi star squared for this function. This is because this is our function right here. It's not always squared. This is our function, which with this xi star, this is going to be 9I squared over n squared. Okay, so the Riemann sum definition of the area underneath this curve. So this area right here is what we're trying to compute, right? So by definition, we'd have to actually compute this Riemann sum that we've just worked out the details for. And so that definition would tell us that the integral from 0 to 3 of x squared dx should equal the limit n approaches infinity, sum I goes from 1 to n, and then we plug in our terms here, right? So this is going to be 9I squared over n squared times delta x, which is times another 3 over n. And this takes some work to compute. So, recommended exercise, RE, I recommend that you try this, but try to work out this limit. Okay? But if we know the fundamental theorem of calculus part 2, then actually what we can do, and this is a pretty nice function, we know how to find the antiderivative of this, right? So I'll make this a double arrow here. The antiderivative of x squared is 1/3 x cubed, okay? And the fundamental theorem of calculus part 2, FTC part 2, this then tells us that instead of doing that whole Riemann sum argument right there that we just made, instead of doing that, we can actually just plug in this antiderivative, 1/3 x cubed, and then we can plug in our boundary points, x equals 0 and x equals 3. Okay, and this notation right here just means plug these in for x, and so we get 1/3 times 3 cubed minus 1/3 times 0 cubed, and I'll write on top of my graph here, but that is of course 9 minus 0, so that's just 9. So the area underneath this curve is just 9, but the FTC is just a couple lines of work. As far as the Riemann sum definition goes, you're going to do it. It's a lot more work. You will get the same answer, but it's a lot more work.